Hey, welcome back once again. Last time we saw how an inductor disrupts the MOSFET switching. But there are much more to that. This time we'll see the avalanche breakdown in the MOSFET. So let's start. We need to understand what the breakdown of a semiconductor is and how it occurs. Let's say there is an p-n junction of a semiconductor. When it is reverse biased, a very small amount of current flows to the p-n junction. But when the reverse bias voltage is increased across the semiconductor above a certain limit, a large amount of current flows through it. This phenomenon is known as reverse bias breakdown. The voltage at which the breakdown of a p-n junction occurs is called as reverse breakdown voltage. There are two types of such breakdowns, which are known as avalanche breakdown and reverse breakdown. In this session, we'll see how a MOSFET goes under an avalanche breakdown and what happens to the MOSFET when it goes to avalanche breakdown. Avalanche breakdown in a MOSFET occurs where a fallback voltage generated during the turn-off of an inductive load during MOSFET switching or a spike voltage caused by a parasitic inductance present inside the circuit exceeds the breakdown voltage of a MOSFET. When avalanche breakdown occurs, the p-n junction of the MOSFET is reverse biased. Well, this avalanche breakdown in MOSFET occurs due to three modes. First is the degradation of Avalanche ruggedness due to dV by dt. We saw what is dV by dt rate in a MOSFET switching. An excessive dV by dt rate might cause problems like fault switching, oscillation, or permanent damage of a MOSFET. If we see the structure of a MOSFET, it looks like this. But there are parasitic diodes, NPN transistor and capacitor due to all N and P substrates present inside the MOSFET. If we see the actual symbol of the MOSFET, it looks like this with an intrinsic capacitor, diodes and NPN transistor. The NPN transistor is present between drain and source of the MOSFET. When the drain to source voltage changes rapidly during the turn-off process of a MOSFET, its parasitic NPN BJT might exhibit a fault switching, making the MOSFET vulnerable to secondary breakdown and eventually permanent damage. If we see this equivalent symbol, the drain to source voltage changes rapidly during the turn-off process of a MOSFET. The dV by dt in the drain to source voltage causes a varying current to flow through the p-n junction capacitor and resistor. This current is expressed with this formula. This current I causes a voltage drop across the intrinsic resistor, which is applied across the base and emitter of the parasitic bipolar transistor. This transistor turns on when the voltage drop exceeds its base to emitter voltage to turn on. The larger the dV by dt rate, the larger the current, the larger the voltage across base and emitter becomes. The larger base to emitter voltage makes the parasitic NPN bipolar transistor more susceptible to false turn on. At this time, if the drain to source voltage of the MOSFET is high, the parasitic NPN transistor might enter into secondary breakdown, causing permanent damage to the MOSFET. Second is avalanche current breakdown. This NPN transistor turns on due to capacitor. But if we see the previous MOSFET structure and check its equivalent circuit in the MOSFET symbol, this diode D1 also plays a very crucial role in the dV by dt switching rate. We learned about the reverse recovery of the MOSFET in last video. Please click on this card to know more about it. While MOSFET switches, just like freewheeling diode, this intrinsic diode transitions from freewheeling mode to reverse recovery mode. In reverse recovery mode, the drain to source voltage of the MOSFET rises. The diode's recovery current and recovery d by dt might cause the current to flow through the diode. And due to that, voltage will generate across base and emitter of the intrinsic transistor. If this voltage generated across the resistor is high enough, then there will be false turn-on of the parasitic NPN transistor in the MOSFET and cause a permanent damage. Third is the avalanche energy breakdown. Well, when avalanche behavior causes a MOSFET to enter the breakdown voltage region, current continuously flows from the drain to source of the MOSFET until the energy stored in the inductor is fully consumed. Because of the current and voltage, a power loss occurs. This energy causes the device temperature to increase and causes permanent damage to the MOSFET if it exceeds the rated channel temperature. We know power MOSFETs are commonly used in high-speed switching devices. A power MOSFET experiences a high voltage spike between the drain and source during turn-off due to the circuit inductance and strain inductances. Let's consider the circuit inductance and strain inductances BL. Then the surge voltage will be is equal to L into di by dt. If the drain to source voltage of the MOSFET exceeds its breakdown voltage due to surge voltage, an avalanche current flows to the MOSFET. If this current exceeds the current or energy limit of the MOSFET, it can cause permanent damage to the MOSFET. Earlier, surge absorbing devices was used to protect the electronic devices, but nowadays we don't use them to reduce the number of parts and thereby the size of a system. Well, we have to fulfill this requirement of the avalanche. So, a power MOSFET needs to damp this avalanche energy even in the event of voltage surge exceeding its voltage rating. This avalanche energy carrying capacity is mentioned in the datasheet of the MOSFET under avalanche rating. However, avalanche event place an excessive stress on the MOSFET. Well, the capacity of the MOSFET to damp this avalanche energy is known as avalanche ruggedness. There are two types of avalanche ruggedness, which are named as repetitive avalanche ruggedness and single shot avalanche ruggedness. We'll see those in the future videos. Till then, stay tuned. I've added all the reference on this topic in the description. I hope you got something from this. If you haven't, you can watch the video again. Still, if you don't, you can ask your doubts in the comment box below. Hit the like button if you like this video, subscribe to my channel, and finally, thanks for watching.